Hello, my name is Kyung-Min from the Pohang University of Science and Engineering in South Korea. I'd like to introduce our research about the emergent constraints for future changes in Arctic phytoplankton using CIMIC 5 and CIMIC 6 Earth system models. The human-induced climate changes are frequently observed in the global Earth, and this global warming trend will be projected to be amplified in response to the future climate change scenarios. Particularly, the Arctic regions has warmed more than twice as fast as the global average, known as the Arctic amplifications. As a result of this sensitivity, Arctic Ocean has experienced the fast sea ice decrease and the strong stratifications. These physical changes induce the other biogeochemical changes that nutrients will be decreased in response to the intensified stratification. And also the reduced sea ice allows the additional light supplies to the ocean, and these two factors are both important for the phytoplankton growth. These physical and biogeochemical projections are showing a large intermodal spread that the estimations of the future marine productivity in the Arctic Ocean has still large uncertainty. This primary prediction is simply calculated as the product between the amount of the chlorophyll and the light availability. So we need to estimate the future changes in chlorophyll accurately to estimate the primary production more accurately. In previous study, the Lewis et al. Represented the research about the Arctic MPP in recent 20 years. During recent 20 years, the Arctic MPP is continuously increased, and these increases are sustained by increased open ocean area in first 10 years and by increased by chlorophyll in second 10 years. This research implies that the estimations of the future changes in chlorophyll is more important because the decline of the sea ice is obvious and even be faster in future climate. To investigate the future Arctic chlorophyll changes, we used the Earth system model outputs participated in SMIP 5 and SMIP 6. In this research, first, we analyzed how the Arctic chlorophyll will change in response to the global warming, which is important for estimating the Arctic primary production. And second, we investigated what factors will be more important for the chlorophyll changes. And last, to reduce the large uncertainty of the future chlorophyll projection, we estimated the future Arctic chlorophyll changes by using the emergent constraint method. Left two figures show time series of chlorophyll and nitrate average in the Panarctic Ocean. In previous SIMI-5 models, the chlorophyll is projected to be decreased in response to the depletion of the nitrate. Although the CIMIP6 model showed the same depletion of the nitrate, the CIMIP6 chlorophyll projections show a large intermodal diversity. Even some models are projected to be increased. Arranging the models in order to the mean chlorophyll changes, the models are divided into the chlorophyll increasing and decreasing models. When nitrate is arranged in the same order of the chlorophyll changes, a relationship between chlorophyll and nitrate changes is not clear. Therefore, we need to find out what other factors drive this large uncertainty in chlorophyll projections. To find out the reason why the chlorophyll projections show a large intermodal diversity in SNP6, we divided the models to three groups: SNP5, SNP6 negative, and SNP6 positive, depending on the future chlorophyll changes. Above three figures describe the spatial pattern in chlorophyll changes. Three groups all show the homogeneous pattern in chlorophyll changes, that the uncertainty of the chlorophyll projections are not caused by specific regions, but influenced by the characteristic of the individual models. The below three figures describe the spatial pattern in the nitrate concentration, climatology, and histochemical scenario. In CMIP6 positive models, the amount of the background nitrate is relatively higher than other groups. Therefore, it was confirmed that the nitrate mean states rather than the nitrate changes are much important for the chlorophyll projections in future climate change scenarios. To show why these different responses are generated, we need to check out the equation of the phytoplankton growth in models. The equation of phytoplankton growth is usually expressed as the prognostic equation using growth and loss terms. The growth term simply consists of three limitations: temperature, nutrients, and light. The phytoplankton can grow well under the environment of the warm temperature, abundant nutrient, and light availability. In general, strong limitation is defined as the bad environment for the phytoplankton groups with little light and nutrients, and the value of the limitation is close to zero. In contrast, weak limitation is defined as a favorable environment for the phytoplankton growth with abundant light and nutrients, and the value of the limitation is close to 1. In a warming climate, the chlorophyll projections are separated in months depending on each group. We can easily find that the high intermodularity only exists in the boreal summer JJA season. Comparing the seasonality in chlorophyll changes, the model shows the consistency in increased chlorophyll in winter and spring due to the reduced sea ice area. However, the three groups show some different patterns in summer. In SMIP 5 and SMIP 6 groups, the nutrient limitation becomes stronger from spring to summer, which implies insufficient nitrate for growth. However, in SMIP 6 positive groups, the nutrients are still abundant in summer season compared to the spring season, that the nutrient limitation is still weak. Therefore, we can suggest that the nutrient limitation in summer diversity plays an important role in controlling the diversity in future Arctic chlorophyll changes. We define the light and nutrient limitation as an area of sea ice and the amount of the nitrate. The time series of the Arctic mean limitation is shown on the right figure. The light limitation, the blue lines, becomes weakened in response to the sea ice decline. In contrast, the nutrient limitation, the red lines, becomes stronger due to the enhanced stratifications. We checked these limitations in SIMIP6 individual models. The circle and triangles represent the historical and SSP scenarios respectively. In a warming climate, the nutrients become depleted in all models. The SIMIP6 negative models show the decreased chlorophyll with the decreased nutrient. However, the SIMIP6 positive model shows an increased chlorophyll despite of the decreased nutrient. This can be explained by the light limitation. The chlorophyll is increased only in response to the additional light in SIMIP6 positive groups. Therefore, the total limitation, the product between the nutrient and light limitation, show a linear relationship with the chlorophyll changes. So we can explain the chlorophyll changes by these two limitations. We compare the two limitations in Hall-Moller diagram in SIMIP6 positive and SIMIP6 negative groups. In SIMIP6 positive group, the weakened light limitation in response to the sea ice reduction drives the chlorophyll increases because the nutrients are abundant. However, in SIMIP6 negative models, although the lights are supplied more samely, but the nutrients are not enough for the phytoplankton growth that the chlorophyll are projected to be decreased. Therefore, from this Hall-Moller diagram and scatter plots in the previous slide, we can conclude that the supply of the light driven by the climate change only contributes to the increased chlorophyll if the nutrient limitation is weak enough. Lastly, the left figure shows the relationship between background nitrate concentration and chlorophyll changes in multimodal space. The two variables are highly correlated with correlation about the 0.83, implying that background nitrate is important for predicting the future chlorophyll changes in the Arctic Ocean. Applying emergent constraint method to this linear relationship with in-situ-based observations, the future chlorophyll changes are estimated about 30 to 40% decrease, and the observation-based estimation is about 20 to 30% greater than the decrease of the SIMIP projection. Based on the emergent constraint, we compare the cumulative density function of the chlorophyll changes. Before the constraint, the probability of decreased chlorophyll is about the 64.1%,
and this probability of the decreased chlorophyll rise to about 95% that the uncertainty of the sign in the chlorophyll change is reduced about 30%. In this research, we analyzed the future chlorophyll changes and the uncertainty of these changes. Our take-home message is first, the uncertainty of the Arctic chlorophyll changes is increased in CMIP 6, and the background nitrate concentration plays an important role in determining the chlorophyll changes. Second, based on the emergent constraint, the uncertainty is reduced and future chlorophyll changes are estimated to decrease about 30 to 40%. This is the end of the presentations and thank you for your listening.